Yes, my name is Linn Saarinen, and I'm working at Vattenfall Hydropower as a technical specialist in frequency control and turbine governors and other system issues. I was asked to talk about something with this heading, delivering flexible power and ancillary services with hydropower. So that's what I'm going to do. Hydropower. Very often we talk about hydropower as a master of balancing. It's in electrical engineering courses in the university, and many people have this image of hydropower that it's really good at balancing. But there's another image coming up now that maybe that hydropower is actually responsible for bad frequency quality in the system. So I will try to talk a little bit about these two views of hydropower and why we can, in a way, say that both of these things are true in their own way. So starting with master of balancing. One reason why hydropower is so good is because start and stop is very quick for hydropower, while thermal power takes a long time to heat up. It can take many hours to start. For hydropower, it's usually a matter of minutes. So going from full stop to full load is quick. Also, when we regulate hydropower, in most cases, we have reservoirs in the river, so we can save the water that we are not using. It's not as for wind power, for example, if you regulate down, the wind is just spilled, you can't use it. But for hydropower, if you have a reservoir, you can save it. And in Sweden, most of the hydropower, at least large plants, have reservoirs. Another factor is that normally maximal efficiency is not the same as full load for hydropower. So if you want to run your unit on maximal efficiency, you still have a margin for up regulation and down regulation. Regulation speed is quite fast to normally, at least in our stations, we have 1% per second for ramping of power, which is quite fast. So what is the downside? Why is it not good at regulating then? Well, Evert and Andreas, I think, have already talked about this effect, non-minimum phase response. And what is that? It means that if you try to increase power, you will first get the response in the opposite direction. So if you want to increase, you get a decrease, and then an increase, and the other way around. If you want to decrease, you get first an increase. And it's because you have to accelerate the water in the waterways before you can actually get the power out. So the initial power that you try to get out, it's spent by accelerating or decelerating water. So that's one part. Then another part that also Evert talked a little bit about, or no, maybe he didn't talk exactly about it, but output power from a hydropower unit, it depends on the head. And the head is something we can't control. It depends on how other units in the river have been run or operated before, and also how you have operated your own unit in the past. So, that's the head. So the head is the difference in water level above and below the hydropower unit. So the head varies over time, and then also when you do a change in your own unit, you get variations in the head, that is surge in the waterways. So normally we have two different periods of this surge. One quicker, that is 10 to 15 second period, which is surge between the surge gallery and the gate shaft, of the unit, and then we have a longer period, which is a surge between the surge gallery and the downstream water level. So these two, these surge head variations are also something that we can't control. They are triggered by any changes in the water flow through the turbine. Yeah, so we have those, and then nonlinear relation between guide vane opening and output power. That's what Evert talked about. That we changing the guide vane opening a certain percentage is not the same as changing the power a certain percentage. And then backlash in the regulating mechanism, which also Evert talked a little bit about. And that phenomenon with backlash, it's amplitude dependent and it's nonlinear. So yeah, this picture, if you're not familiar with it, it's part of the regulating mechanism for Francis turbine. So we have here the guide vane. Is it called guide vane ring? So guide vanes are down here, and one of the servos that operates this ring and thereby opens or closes guide vanes. So this mechanism is something that has backlash in it in its operation. Let's move on. Here are some examples of results from testing of hydropower response. So you have 3 units here, unit 1, B, and C, which is, this one is Kaplan-like, not exactly Kaplan, but, and these 2 are Francis units. And there are 2 things I want to point out with these responses. The first one is this non-minimum phase response. So we get the response in the wrong direction. In my experience, this happens for Francis turbines, but not so much for Kaplan. So you see here, we don't really see any non-minimum response for this one. It's just more like a delay and not so much non-minimum phase. And then we have this phenomenon, which is backlash. So, okay, I didn't mention that the blue here is guide vane opening change, and the red is output power in all the graphs. So the guide vane opening follows sine here, and this sine comes from sinusoidal grid frequency test signal. And the power also follows this sine, but not really, because here it's sort of disrupted by moving. When it changes direction, it is subject to the backlash, so nothing happens for a little while before it starts to regulate again. So you can see it here as a little bit of a plateau. This one does not have the same behavior, really. It's much more sinusoidal response, and this one has a large plateau here. So some other test results. We have made a few tests with the new technical requirement, the tests that are prescribed in the new technical requirements for FCR-N and FCR-D. And this is one of these FCR-D tests that we will, at least in the previous version of the requirements, were supposed to do. So the test is basically start at 49.9 hertz. That is when the FCR-N is totally outregulated, and then take a frequency ramp down. It's actually a little bit too much. It should only be 1 hertz, so down to 49. But this is a little bit too much. But 300 millihertz per second ramp, and then measure the response. So here is guide vane opening response. runner angle opening, runner angle response, and power output. So this is a Kaplan unit with where you can regulate both guide vanes and runner blade angle. And then EP1 and EP2 is just two different settings for how much gain this unit has in how much controller gain. So delivering different amounts of regulation, so to say. So here we say, okay, guide vane opening, that one follows quite closely this ramp of the frequency. It's responding fast, actually. But we see also that it saturates at some point. In this case, it saturates at 75% because that's a limitation for this unit. And then even though this red one should have had a double steady state response, it also saturates at the same point. So you don't get all of that in practice. And then the guide vane, the runner angle is much slower. And that is what controls actually most of the power output. So you see power output follows more this ramp of the runner angle than the guide vane opening. And it's much slower than this ramp that we had in frequency. And what's more important for when it comes to FCR-D is that the requirement for FCR-D is, or the amount that will count in the new requirement is what you can deliver in 5 seconds. That's the important number, like how many megawatts in 5 seconds. And as you can see, in 5 seconds, there is very little from this unit. And then we have, we have regulated from 55% to 75% very quickly, but still the power output is not much in 5 seconds. And the steady state level is much higher than what we get out. So this is a problem when it comes to hydropower delivering FCR-D. Yeah. Wrong direction. So the FCR-N tests that are prescribed in the new technical requirements, it's sign-in, sign-out tests. And this is some results from the such FCR-N tests. Here you can see that the phase shift calculated from sign-in, sign-out tests on the unit is larger than expected. So the expected is the simulated values that are dashed. It's what our model told us that we would get. And then we have the measurements, which is the full line here. So we have like almost 20 degrees more negative phase shift than we would have expected. And then this model is still, it has data from the unit. It's not just, it's a model that's supposed to actually describe this unit, but there's still a lot of difference. And the problem with this phase shift is mostly these points. When we get to short period times or high frequency, this phase shift will make the system unstable. If we pretend that this unit delivers all the frequency control, if it's scaled up and delivers all the frequency control to the system, this large phase shift at these period times would make the Nordic grid unstable, or at least not within stability margins that are prescribed. So we would be maybe not unstable, but not. We wouldn't have the margins that we need according to the requirements. So why is this a problem? Okay, I have more explanation on the next picture here. So what we are measuring in this test is this system. it's the grid frequency deviation that we put into the governor, and then the unit reacts, turbine and generator, etc., reacts, and we get an active output power response. So this is an open loop system, only our unit. And with an open loop system, you typically get this kind of Bode plot. So this sine, sorry, this is in Swedish, but it's input signal and output signal. The input signal is a sine, and the output signal is also a sine, but with a certain gain here, which is larger than 1 in this case, because we get more than it's larger than the input. And the phase shift, how many degrees is it delayed, which we plot like this as a point in this phase shift diagram. So if we increase then the frequency or the decrease the period of the signal, we typically get less gain and more negative phase shift. This is typical for low-pass systems, which is many systems in our reality is low-pass characteristics. And then if we increase the frequency even more, we get even less gain and also more negative phase shift. Let's see. And the critical point, so to say, of this system is if you get so much negative phase shift that you come a whole half period too late with your response, then you will start to increase instead of decrease the disturbance, and you will have an oscillation in the system that will just increase in size, and then it will break down. So, and that happens if you draw it like this. If you in the system have 180 degrees phase shift and gain that is larger than 1 for the whole system, then you have increasing amplitude and unstable system. So that's what we have to watch out for. So looking at the closed loop system then, we have the same system we had before with the frequency to active power, but we close the loop with the power system and feedback this frequency. What happens to this Bode diagram that we measured on the open loop system? Then we get this type of response instead, the same sinusoids. Yeah, I'll take all of them. So this point that was in the open loop system was up here somewhere. It comes down, the gain will be less, and the phase curve will have this kind of will look like this. And in the closed loop system, what we don't want is to have a large peak here. This peak corresponds to coming closer to this instability point where any disturbance is increased instead of decreased. So so the peak here is the problem, and if we have bad controller tuning, then we will get a larger peak here. So any disturbance with this frequency that we have in this peak, if the load or another power source varies with this frequency, then that will have a large impact on the total system grid frequency. It will be very visible or even increased. So this was a little quick crash course in Bode diagram, just to make sure that you follow how these technical requirements work. So where are we now then in the system? Are we close to this problematic point in reality or not? It's a good question. In, was it 2014, we did a full-scale test in the Nordic system to see, can we actually see this behavior that a small disturbance can get large frequency deviation if it has the right period. So here is the power disturbance, plus minus 50 megawatt, created at the hydropower unit. And here is the frequency response to this disturbance and the power flow between Sweden and Norway and between Sweden and Finland. And the corresponding Bode plot for these measurements. So the model has this peak, as we saw before, and the measurements where we put a power disturbance with varying frequencies or varying period times to the system and measure the response also has this peak. So it's clear that this the concept of this model is correct. This is how we can actually measure it in the reality. And it's not a lot of power that is needed. Plus minus 50 megawatt is quite enough to make and have an impact on the grid frequency if the period is 60 seconds. Yeah. So and we can say that this peak that's it's hydropower that is the culprit for creating this one because of this negative phase shift that we have from hydropower. Yeah, and another thing to keep in mind with this is that when we have this relatively fast, not very fast, but 1 minute period time disturbances like this, the power regulation from hydropower units and other units that have this setting in the governor with 60-second feedback constant, the actual power output, let's see. What's wrong with my figure? It shouldn't say frequency deviation here. Oh, yeah, okay, frequency deviation. If we assume that we have this power disturbance, and if we got the response from the steady state gain, like how much regulating power do we have, like 600 megawatts FCR-N, if we should get the full response at this for this disturbance, it would be this blue curve, which is quite a lot. But in reality, we only get this little. My titles are not good here, I realize. I don't know how I thought when I wrote that, but and that's because 60 seconds is too short a time for the governor and the unit to actually get power out. It's only a little fraction of it that actually gets regulated. So the active regulating strength is much lower when we have these periodic disturbances in the power. And I think that is something that it's easy to forget, because I mean, maybe we tend to think that, okay, this control, the frequency control, it has a time constant of 60 seconds. Okay, then it should mean that it actually regulates. I mean, it should be active when the disturbance is 60 seconds, because it's the same number, you know. It should be, we should get some regulation, but actually that just means that it starts sort of to act when the disturbance is 60 seconds, but it's still a very little. So you should need to have a much shorter time constant to actually regulate a lot for the 60 seconds. So, okay, I have arrived at the summary. Hydropower, the strength when it comes to regulation is large available power reserve. We can regulate a lot with hydropower. And also we have a large available energy reserve. We can maintain the power output. And it's relatively fast. But the weakness is that we can't deliver much in 5 seconds. And we have this negative phase shift that is making regulation on the time scale of 1 minute and faster not good, even up to maybe a few minutes. The regulation is not so good. So what is needed then to complement hydropower? I mean, it can do a good work, but something else might be needed. So as I see it, a small, fast, continuous response that can take on all these small variations that hydropower can't follow and balance them. And then, on the other hand, a fast and large response to large disturbances, because that's also something hydropower can't do, to react really quickly when there's big disturbance. But then again, these complementing responses don't really have to be persistent to be useful. Since hydropower can come in after a little while with a lot of power, actually what's missing is something that can take on these disturbances for a shorter time and not necessarily keep up in the long run. That's about it. I just added one more slide about the new regulations. Apart from what Andreas talked about with new technical requirements, we also have this new regulatory landscape with the RFG and EIFS, Energimarknadsinspektionens föreskrift. And I think I wanted to mention this because I see that this is very problematic, that we have this. These are requirements for being connected to the grid, and it's requirements that is valid for new production units, but also sometimes in some occasions they can be applied to existing units if they are rebuilt in some way, and we don't know really when it will apply. But these are some requirements that will be hard, I think, for many existing units if they have to fulfill them, and maybe for new units too. So power response to frequency deviation in 2 seconds. It's stated in the RFG. I mean, it has to start within 2 seconds. And that, yeah, some units can do it, but not all. It depends on the waterways. Also, 10% power response in 5 seconds for Kaplan units and 20% for Francis. I think this is also very difficult. And then droop to 12% and insensitivity to frequency deviation of 10 millihertz. If you combine this 12% and 10 millihertz, then you get 0.17% regulation, and that's very small. It's comparable to the backlash. It's for many units probably smaller than the backlash, so we can't probably in many units we can't be sure that we will deliver anything for 10 millihertz, but we are required to do it. So yeah, wanted to lift that question as well. So that's.
Give Linn an applause. Thank you very much for a really good presentation, and I think it's really good that your last slide here is lifting up the new requirements for. They are applicable mostly, or the thought of it is to be applied to new power producers and demands as well. But we really need to have a discussion about the requirements and how they are supposed to be so neutral as possible. And it's really hard to write them, and then we're going to apply them to different kind of power producers, hydropower, nuclear, and so on. It will be a challenge, but we need to face that, and we need to do it together with the industry as well. Anyone who has a question for Linn? In the back.
Thank you, Linn, for a very good presentation. You said you wished a fast, continuous response.
Yeah.
What could that be?
Well, it could be. I think it could be maybe nuclear could provide it. Batteries, other fast sources, and I think many of these maybe don't have the ability to maintain power for so long time. And then I think that really that shouldn't have to be a problem, because hydropower can do that. But if I can jump into this FFR discussion and say something about that, I think I mean it's really good. It solves one of the problems to have FFR, which is like a step response when there's a big frequency deviation. It solves half of the problem, which is managing system stability when there's a large disturbance. But the other half of the problem is continuous regulation. And then I think we really need something in that part too, some fast response that can tackle these small deviations and do it, actually sort of replace the load frequency response, or what is called load frequency regulation, damping, that we have had in the system that is maybe decreasing.
Yes.
To have something else that acts this way, or like inertia. So I think because if we don't get anything that acts continuously, then we will have more and more oscillative grid frequency, and hydropower will have to regulate more and more,
Yes.
but not regulate more, get more wear and tear, but not actually getting a better frequency quality. I think it will just be decreasing quality. So,
Thank
yeah.
you for a very good answer. Thank you, Linn.
I was wondering how many governors for the hydro turbines that are digital governors and how many are mechanical governors. Would that make a difference in regulation speed?
I think most are digital nowadays.
Okay.
Maybe some small units have mechanical governors, but I mean in Vattenfall there's I think almost only digital governors at least in the large plants. So.
Okay.
Okay.
Hi. The Swedish system does not have any dead band in the frequency response. Do you think we should introduce it for this continuous response that you talked about? It might help or not, and.
I think if we get that kind of fast continuous response, it should not have a dead band. It should act right away and balance the small deviations. If it has a dead band, I think the use of it is much smaller. It wouldn't have as much benefit.
But do you think it's worth to introduce a dead band? Because it's one of the few systems in the world that doesn't have a dead band.
I don't think it's good to have a dead band. I mean, there's also two types of dead band possible in units. One is a dead band around 50 hertz, a fixed dead band, to say that if you're close to 50 hertz, don't do anything. And then the only thing that will happen if you have this is that you will never be in that inside that dead band because no one is regulating. So you will always be on either on either side of it. So I think that's not a good idea. It's only a good idea if you want a specific reserve not to regulate in this band, but you have to have something doing work there. The other type of dead band is for a unit if you have a floating dead band that follows the frequency, so it acts more like a backlash of the unit itself. So if we are increasing power and then we should decrease a little and then we will increase again, then we just skip this little small ripple and stay and continue upwards. And that type of deadband is reasonable from a unit perspective because it decreases wear and tear. But it's not very good for the system. It's not necessarily so bad either. It decreases the efficiency of the control a little bit, but if it's small, it could be okay. So it also depends which deadband you're talking about, if it's this one.
So any more questions? Oh, Monica?
Thank you. There's a lot of talk about the new environmental demands affecting like the active power flexibility. Does that have any impact on the ancillary services?
With the Water Framework Directive, for example. I don't think it has a lot of impact actually on the ancillary services. It could have an impact if you depends. Yeah, I don't think it has so much impact actually on that. It's more on larger regulations for a longer time, like day to day and weekend to weekend. I mean, that is regulations that are controlled by the market, so to say. That's I think the major part that it affects.
So we have time for one more question, I think. Jonas?
Just want to say thank you, Linn, for finding the backlash for the industry. You are the not founder of the backlash, but the one that investigated the backlash.
I'm co-founder together with some other people here, Per and Evert and others.
Thank you very much.
Fantastic. Thank you, Linn, for your presentation. Really good.